So welcome to Quantum Magnetism. I'm going to give 5 lectures on different aspects of magnetism here. And most of you will have done courses on magnetism before. So some of the things you'll have seen, I'm sure, before, but hopefully there'll be some new things for you. And this will be maybe a different approach to what you've seen before. So let me tell you about the approach we're going to take. So here's actually the 5 lectures. So today I'm going to give perhaps an hour on number 1, that's the magnetic moments and susceptibility, and then number 2, fluctuations and dissipation and response, with about 50-minute pause between the two parts. And I've put the 2 references that I've used for the course here. There's Quantum Theory of Magnetism. That's a nice textbook, a more advanced textbook on magnetism by Robert White. And then Steve Blundell's undergraduate or master's textbook on magnetism has a lot of the things that I'll talk about in as well. So today's lecture is going to be about these 2 quantities here that I've written. Let's just see if this is working. Something's happened there. Okay, so the magnetization and the susceptibility. And the first couple of lectures, I just want to show you how you think about these things in what you call a stochastic approach, which is interesting to understand many aspects of magnetism, particularly scattering and sometimes excitations and many other general properties. So what we're going to do is just think of the magnetization as a variable that fluctuates in time in the system and in space. And I'll show you, and one can define magnetization. We'll do that in a minute formally. And then I'm also going to talk about the susceptibility that goes with it. So when you're talking about a magnetization that varies in time and space, you have to generalize how you think about susceptibility. Of course, the susceptibility is a response to an applied magnetic field. So normally we think of susceptibility as just being the response to a static uniform field. But here we're going to think about how the system would respond to a magnetic field that varies in space and time. Okay, so a few preliminaries then to make us able to understand these things. The first thing is how do we define the moment and where does it come from? So if we just think of individual atoms in the material to start with as points, each one we could have a magnetic moment, I've drawn that here to illustrate what's going on. One can add up all those moments to give you a total moment, which will be a vector in a certain direction, and obviously that's what you can measure, say, in a magnetometer or something like that. One can define a magnetization, which is the moment per volume, and in electromagnetism, this is the magnetization that you know and love from the first years of your undergraduate courses. But now we're going to just think of this magnetization varying microscopically in space. So one can do that. So one can think of the magnetization as a local variable then, okay, m of r. So we'll look at that, what it actually looks like. Now, to make things a bit more rigorous, you have to define over a small volume and work out the local magnetization in a limit. So this would be a small moment over a small volume here. Okay, and now let's just recall that if the system is agitated by thermal fluctuations, or there's quantum mechanical effects, then the moments, the local moments, if we look at small enough volumes, will be fluctuating away. So I've just drawn you a wave of magnetization in space and time there. Let's not worry whether it's space or time at the moment. So we think of this magnetization then as a stochastic variable. So what we could do is to also work out its Fourier transform in time and or space, as I've defined here. I've defined the full complexity here of Fourier transform. So we've transformed with respect to time and space, and we can also think of this magnetization as this function here, which is basically the spectrum of the magnetization or the magnetization fluctuations. So we'll have a look today at some possible things here, possible spectra. Okay. By the way, if you have questions, you can interrupt me, and I'll give you a chance to ask them at the end as well. All right. Okay, so let's just think about a constant constant magnetization here. So this could be a snapshot at a particular time, or an average over time, actually. So in reality, the magnetic moments on atoms are spread out in space. They're not just point things, as I used in my illustrative example at the beginning. They're spread out in space, and typically atoms will have certain electronic orbitals, which the number of say spin ups and spin downs are not the same, or they'll have an orbital moment. So the distribution in space will be connected with this orbital that the magnetic moment is sitting in. So here I've illustrated what one might have in a solid, going through the solid now in space, and these are different atomic sites, and around each one you've got some cloud, if you like, of magnetic moment. So one question is how you measure that and what it looks like. So this is, if we imagine this to be just an ordered material, such as iron or something, which has a magnetic moment below its Curie temperature, and this is what it's looking like in space, because it's a periodic function, you know, in a three-dimensional periodic function. We can Fourier transform this and look at the basically we get a Fourier series, which is what you normally get in reciprocal space, and we can see that if we were to Fourier transform it, we would get different components to this magnetization at different Q's, and these would be correspond to the reciprocal lattice vectors in the system here. So there should be sort of tau. So we can decompose our moment into different Fourier components, and one could then do a scattering experiment to measure these different components with a probe that's sensitive to magnetization, such as neutron scattering or resonant X-ray scattering, and work out what the shape of these orbitals are. I'll show you some of that later on, but that was just to illustrate the usefulness of thinking of this magnetization being spread out like this. Okay, let's just have a look at the traditional susceptibility and magnetization to see how it connects with the things that I've been telling you about so far. Okay, so the magnetic susceptibility then, in the case where we just have a uniform field and a uniform magnetization now, so we're just averaging, it's just defined as m over h in SI, or m over m times u naught times b. I'll be a little bit lax in what I'm talking about today, and not worry too much about this factor here. Okay, so if we're looking at the susceptibility, then just to make contact with other courses, then we can define we can also normalize to mass or various other units of susceptibility. So when we're looking at these magnetization fluctuations and so on, it's often useful just to use Bohr magnetons as our basis for the moment. And so, for example, you would have Bohr magnetons per formula unit or per atom, and the susceptibility would be the ratio of this magnetization in Bohr magnetons per formula unit to the field. Okay. So in some sense, the Bohr magnetons per formula unit is an M, because this formula unit also defines a volume in the system. Okay, so just some boring susceptibilities here of different metals, showing you that some of them can be quite temperature dependent. Okay, so now let's go from that susceptibility to the more general case, which I was mentioning at the beginning. So let's imagine that we have our magnetization now, which is a microscopic magnetization, varying, for example, in space. We'll imagine that it's just a wave like that, for example. And let's imagine now that this magnetization that we've got here, that we're interested in, has arisen because we've applied a field to the system. And in this case, here is the field varying in space. So this is a thought experiment to start with. If we were able to put little magnets microscopically, we could define a field varying in space, and the system would respond to this field. And instead of having a uniform response, which was what I just showed you previously, which is normally what you measure, this time you get a response that varied in space. Okay, so one can think about that as being a generalization of the susceptibility. It's a generalization in the sense that we've gone from basically Q equals 0, the uniform case where the field that we apply would be a constant, to Q not equal to 0. So that is usually called the generalized susceptibility. Okay. So to make things even more general, we could apply a field that not only varies in space, but varies in time as well. So I can't draw that, but except let's imagine it's constant in space this time and varies in time. And the same arguments would apply, that the field and the magnetization would both oscillate in time, and we can take the ratio of these two things to define a susceptibility. Okay, so I didn't mention that before. So now we've got these two things, the field which we apply and the magnetization, and we can take the ratio and define a generalized susceptibility like this, which relates these two things. So of course, this susceptibility now includes all sorts of things, right? Because we can go to zero frequency and zero wave vector and get back to our normal susceptibility, which is a static quantity. Or we can let both of these things be finite, and then actually what we're looking at is excitations of the system. Okay, or if we only let Q be finite and we keep omega 0, that's still a static property, and that's the wave vector dependent susceptibility. Okay, so in the rest of the lecture, I'd like to just tell you a little bit about how we measure some of these things. And then in the second lecture, I can just tell you a little bit about actually what this this generalized susceptibility tells you about excitations and how it connects with other things. Okay, here we go. So the static susceptibility, one can just measure in a squid or in a magnetometer in general. So squid is what people use just as a standard workhorse for measuring susceptibility. And here you see the susceptibility of a superconductor. This is IBCO, and as you go into the superconducting state, the susceptibility changes because the spins pair up to form a singlet state, and that reduces the spin susceptibility. And you also create a diamagnetic response in the system. So that would be the Q equals 0 and omega equals 0 susceptibility that you would measure in a magnetometer. So you apply a field and just measure the moments. Okay. Another thing that's often used in characterization of magnetic systems, just in fundamental magnetism, is the AC susceptibility. So then what we do is we apply a field with a certain frequency with a coil. So if we have a coil, put our sample inside, and then we put an alternating current through this. So we got a field alternating inside, and then we measure the response with another coil. Let's put another coil on top, and you get a voltage induced in the second coil, and you use that to measure susceptibility. So how does that connect with what I've been talking about? Well, this is a very simple case. So if you think about what you're actually applying when you do such a measurement, is you're applying electromagnetic wave. Because the field is varying with time, you're applying electromagnetic wave, in this case, somewhere in the light spectrum, as it were. But typically, it would be a very low frequency wave, let's say a kilohertz or something like that. So if you work out the wavelength of such a wave, you'll find that's huge. So basically, over the size of a sample, a millimeter size sample, for example, this magnetization, the magnetic field would be constant. So you would be measuring at low frequency, a kilohertz, but the wavelength of the wave would be essentially infinite as far as the sample is concerned. So it would be a uniform field that's varying in time. And that's often used to measure steps in magnetization. And here you can see some results from measurements on strontium muthnate, a system that shows some metamagnetic anomalies. So jumps in the magnetization as you change the field, and they've used AC susceptibility to find out where those jumps occur. And here you can see the measurements that they've got in their coils. So they apply a field, and then they measure the real part and the susceptibility and the imaginary part. So by the real part, we mean the part that's in phase with your applied field. So if this was the time varying field, and then we have the magnetization in phase, or in general, we might have a magnetization that's, let's draw one that's out of phase. So if it was shifted slightly, that's supposed to be shifted slightly, then one can work out one can think of this as a sine wave, and then there's a sine contribution and a cos contribution to the magnetization here. And the one that's in phase, say the sine one, we would call, we would work out susceptibility, which is the ratio of the the magnetization, the in-phase magnetization to the field, and we would call that the real part, and the outer phase one we would call the imaginary part. So that would be the magnetization that has a cos variation to it. So you can see in this case the red one is the outer phase and the blue one is the in phase, and they look very different. In one you see 2 anomalies, and in the other you see 3 anomalies. We'll see in the second lecture that the imaginary part relates to absorption and dissipation of energy, and that's what these 2 transitions indicate, that there's actually a first order phase transition going on here, which has some dissipation, and that's why these 2 peaks show up. But this one here does not have that property, so this actually isn't a phase transition. Okay, so that was some measurements at with Q very long here, just showing you what the susceptibility means in that limit. Okay, let's have a look at another limit, which is to take the omega going to 0 and look at the wave vector dependent susceptibility. Okay, so here we are, wave vector susceptibility, and we're going to take the real part of that. In fact, so it's just a imagine there's no absorption going on. So the wave vector dependent susceptibility is an interesting thing. So we can calculate this, and you see that in Blundell's book, for example, and also in the white book. They have the calculation for electron gas. So if you have an electron gas with a Fermi surface here, so this is just a free electron gas with the energy is dispersing with Q or with K, probably better, more like K. So this is electron energy, and then it's some Fermi energy, and then you imagine applying a field to the system of different wavelengths or wave vectors, and to look at the response of the system. And this is what's calculated here. This is Q along the bottom, and this is chi of Q along the top. And you can see that for different dimensions, you get different things. So for the 2-dimensional case here, this is how the chi of Q varies with wave vector. And for 1 dimension, which would correspond to a Fermi sort of a line of possible Ks with a Fermi surface of 2 points, you get this here. So you can see, interestingly, that the response is strongest in 1 dimension at 2kF, so across here, and in 2 dimensions there's an anomaly at the Fermi at 2kF. Okay, so that means that this is just a very simple calculation that one can do, but one can learn something quite interesting about it, is that systems, if they have bits of electronic structure that have a 1-dimensional sort of aspect to them, for example, sheets of Fermi surface that are a certain Q apart, or some, let's call it K, I don't know, Kn for K nesting apart, and if there's bits of Fermi surface like this, then you'll get a peak in chi of Q at those, and that's because you'll cause you'll be able to move electrons across and create this response. Okay, so this is the wave vector dependent susceptibility. If one wants to measure this wave vector dependent susceptibility, one has to do basically do a scattering probe, which I'll talk about later in the course. Okay, so far it's been a bit stochastic, just treating the magnetization as a variable that can do anything we want, just a mathematical variable. But let's just spend a little bit of time on seeing what can actually give rise to magnetization on atoms, because fundamentally all this stuff I've been telling you so far has to come from the electrons associated with particular sites, particular atoms. Okay, so if we just take a single atom then and apply quantum mechanical operators to the atom, we've got the orbital moment, the orbital quantum number, we've got spin, and then we can add the orbital and the spin magnetization together and get the total magnetization. So these are the three things that one can use on a single atom to get the different eigen states for the moments. Okay. Now, yeah. So one, of course, can think about the moments in the absence of field, but I'm not really been talking too much about that in this course. So we can have things where these moments will be there. For example, in iron, there'll be a static moment with mostly spin, but a little bit of orbital. So I've been talking more about what happens when you apply a field, the response of a system to a field. So when you apply an external perturbation, then the spin and the orbital moments can change, and you get this change in moment, and divide that by the field, and that gives you the susceptibility. Okay, yeah. So we can we can think of the susceptibility then as arising from an orbital response or a spin response in the field. So let's have a look at the Hamiltonian then of a moment, a magnetic atom in a field. Okay, so in the absence of the field, we've just got some Hamiltonian like this, where these are the kinetic energy of the electrons and the potential energy of the electrons all summed up. So then we're going to add a field, and we can add the field, and then we can write the field using the vector potential here, A, which turns out to be a useful thing to do in quantum mechanics. And if you look in the textbooks I mentioned, then you can see that the Hamiltonian can be rewritten like this. So here's the vector potential coming in here, coupling, and it also the field comes in as it couples directly to the spin. Okay, so this is the just dotting the spin moments with the field. That's how the spin moments couple, and then there's another term here which couples to the motion of the electrons. Okay, so you can expand all that, and I'm not going to do that in this lecture. But basically, what I wanted to illustrate to you is that at the end of the day, for the atomic case, then you get this response to the field has this form here. So this is your unperturbed Hamiltonian, and these are the bits that occur when you apply a field. Okay, so there's three different ways the system responds to the field. The first is the spin moment in the field. So you line the spins, and then there's an orbital moment here, and again you can think of that being aligned by the field. And then there's another contribution here which actually goes as the field squared, which is coming out of this term fundamentally, and this is what we call diamagnetism. So in this case, you're actually inducing a moment that wasn't there before. Okay, so we'll come back to that in a minute, how these different terms look in a solid. But I just want to mention this third one here, the susceptibility, or this third one, the diamagnetic moment, which let's just think about this for a minute. So this one means that the energy associated with this is going as the field squared. Okay, so if we look at that here, so if we have a field squared, and some of the other terms are going actually as the other two terms goes as the field. So we can think of the ones that go as field, that the energy is just this moment, spin or orbital times the field, and the one that goes as b squared, we can think of, we can write it like this, as a half times the susceptibility times the field. So this might seem trivial, but it's quite a useful thing just to remember. So what's happening here is we've got a moment that's induced with a field, okay, and then when we convert it to an energy, then this moment actually is going to interact with your field. So you get a square here. Okay, so that's just connecting things up. So if you have a diamagnetic material, for example, then this the susceptibility is negative. So that means that when you put the system in a field, its energy increases. Okay. And if you had something with a positive susceptibility, then its energy would decrease. Okay, so we've been looking at atoms so far, but and those different terms I mentioned, that's for an atom. But of course, when you come into a solid, it's slightly different. You can get, say, the Pauli susceptibility, which you get from moving spin up to spin down in a metal, that also occurs when you apply the field. So you apply the field, you get a moment, and so forth, and you'll get an energy. If you look at the energy effect of the Pauli susceptibility, it will also look like this. But this time, we would have chi greater than 0, and so the system would lower its energy by applying a field. One can work out susceptibilities from these moments if they're non-interacting, just treating each site with Boltzmann statistics, and one gets a Curie law associated with the susceptibility. So I've just done that here. So that's an interesting thing to note, because you can, that's one way of actually seeing what the moments were or are that you're aligning with the field and have a temperature dependence. So I think that's something you would have done undergrad. Probably something that you didn't address at undergrad is the so-called Van Flick susceptibility. Okay, so now we're talking about something a little bit more complicated, which is a system in a magnetic field, atom in a magnetic field, or a system in a magnetic field. And there's another term that arises where you can get mixing between different states. So in particular, this is for the orbital susceptibility. Suppose we have two states. We have the lowest state with no orbital susceptibility, and one here with an orbital susceptibility. Okay, so these might be, for example, states with angular momentum. So it would be a D state, say in a transition metal. So say in I don't know, in titanium or any of the first row transition metals, there'll be electrons in the D states. So it might be a D x squared minus y state, for example, and it has a particular orbital angular momentum. So it would have L equals 2, and different possible components of L equals 2. So it could have it can have 2, 1, 0, or -1, and so on, different components. So if the ground state had no angular momentum, so it was quenched or something, so here, and then we have another one. When we apply a field, we can mix these states and introduce some finite orbital magnetization, and we see this susceptibility associated with this mixing. Okay, and this is called the Van Vliet or orbital contribution. Okay, I just wanted to point out that that existed. I don't want to go into too much detail about it, but this is sometimes that comes up in many systems. You see this Van Vliet paramagnetism. So in summary, then we've got the 4 types of magnetic response. Then there's the spin, orbital diamagnetism, and then there's more complicated mixing of orbital states called Van Vliet paramagnetism. So these all are there in the single atom, and they take across to solids as well. And this is the whole host of things that we have to measure the magnetization and the susceptibility available, the different types of system. So as I mentioned before, you can do magnetometry. You can actually, so you can look with light. Some effects, rotation of light is affected by whether the system is magnetic or not. So you can reflect off the surface with the Faraday effect, the Kerr effect. Sorry, look at the rotation of light off the surface and see magnetic effects. You can do this with light, but also if you go into the X-ray spectrum, you could get the same effect as dichroism. So that can be used to measure moments as well. Neutrons, the neutron has a moment, magnetic moment, and no charge, so it's very sensitive to measuring magnetism in materials. And you can do diffraction and excitations with that. You can put muons in the system. A muon has a magnetic moment. It's a particle with a moment. It goes into the system, and then it sits at a certain point in the system. And then if the neighboring atoms have magnetic moments on, they'll cause the muon to precess. You send it in with a certain spin, and it sits there. The spin precesses, and then after a while, the muon decays because it's not a stable particle, and then it emits 2 gammas according to the moment's orientation at the time it does that. So by looking at the direction these gammas are emitted, you can actually determine how much magnetic moment it's seen inside the solid. So that's a microscopic technique, another microscopic technique for looking at magnetism. NMR is another one. You can look directly at the nuclei. You can look at the nuclei with an NMR, and they can see the magnetic properties of the electrons around them. And now people do spin polarized scanning probe experiments and spin polarized photoemission as well. and an oldie but goodie is Lorentz microscopy, where you send electrons and they through magnetic systems, and there's a deviation of the electron caused by the magnetic fields produced by any magnetic order. So let's just have a look at a few of those things. Just show you some things you can do. So I like this one. This is something that compound that I worked on a long time ago, which is zirconium zinc 2. And these people, they did neutron diffraction. Remember at the beginning I showed you how you could measure different Fourier components of the magnetization with neutrons, and then you can do that, measure the different components with neutrons, and then you can add the different components back together in 3 dimensions and construct a map of how the magnetization varies in space. And that's what's shown here. These are the zirconium atoms, and this is like a contour map of the magnetization in this material, zirconium zinc 2. You see the zirconium zinc 2 material here. So here there's zirconiums. The zirconiums are on a diamond lattice actually in this material, and this is, you can see this is this is a direction going between the 2 zirconiums here. And the interesting thing about the zirconium zinc 2 is the magnetic moment is distributed really over a lot of space. So it's sort of spread like this. And that's because of the, what you're seeing there is the overlap of certain 4D orbitals from the zirconium. So as far as we know, zirconium zinc 2 is the most delocalized material. So it's a ferromagnet with the moments spread out a lot in space. One could do the same experiment with iron, for example, and you would find that the moment is much more concentrated on the iron atoms. Okay. So some of you might be working on superconductivity or have heard about superconductivity. So this is an experiment done by Wedgwood and Shull in the 1960s with neutron scattering again, where they did diffraction experiment, and they looked at how the magnetic moment varied with temperature in a superconductor. So this superconductor is vanadium 3 silicon, and its TC is about 17 Kelvin here. So this is the superconducting transition. So this is measuring the susceptibility or the moment in this material. So they have a field of about 1 Tesla on. So the probe that measures actually the moment, so you can convert that to a susceptibility. And the interesting thing here you can see is that the spins in a superconductor, they pair up in pairs. So if they're able to move separately, then you get a contribution to the Pauli susceptibility. When they pair up to become Cooper pairs, that disappears because the spins can't behave independently anymore. So they can't respond to a magnetic field. So the spin susceptibility disappears. And this is the drop that they see here, spin. But it doesn't go to 0. They find that in the superconducting state, there's still other contributions left, and these are these dreaded Van Flick orbital contributions, which correspond to transitions between different orbital states in the atoms. But you can see that the effect of the pairing is to drop the spin susceptibility down here. Okay. This is something a little bit more exotic from Jerry Lander here. He's someone that works on actinide materials. This is plutonium. Plutonium is a magnetic system. And this time we're dealing with the 5F orbitals. Those are the magnetic orbitals in plutonium. And you remember at the beginning then I said that if you have an orbital, and then you can measure lots of Bragg peaks, and then you get the different Fourier components, and you can reconstruct how the moment might look in space. So this is what Professor Lander has done here, and his collaborators. They've measured different ones. They've just put them as these dots on this curve. So this is kind of basically Q, mod Q going out here in plutonium. So interestingly, they see that there's the curve goes like this. It has a maximum in it. So if you think about it, a maximum is something a bit unlikely. If you have orbitals that are kind of like this in space, let's call this distance r or something. If it's like a Gaussian orbital, then when you Fourier transform that, you'll tend to get something also like a Gaussian that wouldn't have this dip. So this dip tells you that the distribution of the spin in space in the atom has some is highly structured. It has you know, it actually has to have its own peak as you go through the go through space through the middle of the atom, and that's what they're saying here. Then they're saying that the plutonium actually has orbital magnetism in the in its 5f orbitals illustrated here. And finally, this is another probe for measuring magnetization, which is the Lorentz microscopy. So as I said, if you have electron microscope with your electrons going through something, okay, and then you had microscopic domains that you could see in the microscope, because there's a Lorentz force on the electrons as they pass through, they'll be sensitive to the moment. So you can make images of the magnetization on the scale of, you know, tens or hundreds of atoms with this technique, just to show another way of measuring spatially dependent magnetization. And here's a picture of a perma-alloy done here. Okay, so the I was going to give you a preview for the next lecture, which is going to be a little bit different on fluctuations, fluctuation dissipation theorem. So the connection between fluctuations and response functions. So I hope you come to that, and that will be in about 15 minutes. Do people have any questions on the first bit, though? Okay, so I'll start again at maybe 20 to 11, and you can make yourself a coffee or your favorite drink. Would you like to pause, Tom?
Yep, I'll pause it now and go and get a coffee myself. Okay. Yep, recording again.
So in this in the second lecture, I'd like to connect various things here that you might think are unconnected: fluctuation, dissipation, and response. So this is this relates to the magnetism we've been looking at, because we're looking at fluctuations and of magnetic moments. And in physics, when physical quantities fluctuate, you know, one can make some general connections. Just to put things a bit in context, then I'd like to connect the magnetism to Brownian motion and this type of physics. So this is an example of thermal agitation that can be seen with a microscope, which I'm sure you've heard of. So Robert Brown looked at pollen molecules in liquids, and he could see the fluctuation in the molecule as it moved around. It's illustrated by this graphic on the left, where the yellow thing is supposed to be the pollen molecule, and the black dots are the atoms in the liquid, which bombard the molecule and cause it to move around. So if one looks at the pollen molecule, it indirectly tells you something about the motion of the atoms, and then fundamentally the motion of the atoms is driven by thermal agitation. Okay, so analogous way, if we have a magnetic moment in a material, then it too will be fluctuating from thermal agitation. And in addition, I'm going to show you how this connects with quantum mechanics. So it's something that's not really covered at least in Bristol undergraduate, that this connection between the thermal agitation and the quantum fluctuations, and they were found to be part. You can explain them in a universal way, and this was shown by Callan and Wellin in the 1950s, and they discovered something called the fluctuation dissipation theorem, or the quantum version of the fluctuation dissipation theorem. So just to jump forward so that you can see the point of what we're going to do in the next few transparencies. So the Brownian picture there, we had a molecule that was able to move around in its own where it wanted to go. So another example of fluctuation dissipation theorem would be the thought experiment here, where we attach a molecule to a spring to make sure that it can't wander off wherever it wants, but it's still going to fluctuate, because if we put our molecule in a liquid, it will still be bombarded by other atoms. So that's what we have here then. A simple example of fluctuations, and I've got a liquid here, a viscous liquid to be more precise. Well, actually all liquids except superfluids are viscous. So we have a liquid here, and we have an atom or a small sphere inside the liquid with a mass attached to a spring. And if we were to measure the position of this atom vertically and trace it out with time, you might get a trace here, this is its position vertically as a function of time. And I'm going to show you that we can look at this these fluctuations. This is our fluctuation here, this x moving up and down, and we can use some very powerful general tools to say what the fluctuations look like. So I'll show you that, or justify to you that you can get an expression for the spectrum of fluctuations here. So if this is, if we now take these fluctuations and Fourier analyze them, and I'll show you how we can define that in a minute. And this is what we call the power spectrum. So the amount of each frequency, when we Fourier analyze the motion in X in time, we get different frequencies. The power spectrum is described by this equation up here, and it has something like this. The form, it's at high frequencies it drops off with some characteristic width. And these fluctuations, this fluctuation spectrum is connected to the properties of the liquid, it turns out, and in particular the viscosity of the liquid. So we'll come back to that, but that shows you what the title's all about. We've got the fluctuations, the dissipation. The dissipation is coming from the liquid in that example, so that's because it's a viscous liquid. When you pull something through a viscous liquid, you'll dissipate energy. And the response is that we can understand all this in terms of response functions. Okay, but in order to sort of appreciate all of this, we've got to do a little bit of spectrum analysis, do some tools that allow us to understand the properties of fluctuating variables. Okay, so I'm going to use my fluctuating variable is just going to be X, for want of a better variable. So if we just have X of t for the minute, we can have X as a function of spatial variables as well, I suppose. But X you could think of will ultimately be the magnetization, on a site, or the position of the atoms that I've been just describing to you. So if we know X of t, we've measured it in some way over some time, big T, we can define a Fourier transform in this way over a certain time. And one thing about doing spectral analysis of these things is you have to normalize the Fourier transform in the right way. So the correct way of doing it is shown here. So we've got the X of omega. So if we increase t, obviously X of omega would increase. So the correctly normalized spectral analysis function that we will use is defined here. So we do the Fourier transform over the range, we divide by t, and as t goes to infinity, we're going to get a Fourier spectrum from our measured, our physical variable measured as a function of time. Okay, so this is the spectrum, and it's usually called the power spectrum, and that's because it's a spectrum in X squared that turns out to be most useful. And so we're going to take the modulus of this Fourier transform here and square it and write it like this. And it's usually written as in this way, which I'll show you why that is in a minute, or say more about why it is in a minute. But just briefly, this is it turns out we can also write this as the Fourier transform of a correlation function. So people in the field usually call this C because it's coming from a correlation function. The XX means that we're correlating X with itself. Okay, so it's a power spectrum of X squared, if you like, X with itself, and it's a power spectrum in it's a correlation function which happens to be also the power spectrum in omega. So this is the symbol that we'll use for the power spectrum in today's lecture. So that's a simple relationship between the variable, its Fourier transform, and its power spectrum. I've just taken a very simple example here. So just what I've done is to generate some random data, and then I've filtered it so that it becomes correlated with a certain time. So I've done that actually by Fourier transforming it, applying a filter, and then Fourier transforming back. But that's a detail. Here's here's an example of some fluctuations I've generated. Okay, and you can see they're not random fluctuations, because the variable, if you're at a certain point, it's correlated. It's got some correlation with the next point, right? It's a bit like the stock market or something like that. It goes up and down. Okay, so here's some random data, and here I've worked out what the power spectrum of the data looks like. So you can see this is frequency and the 0 here, so it's a symmetric function. So you really only need to look at this time. So it has a sort of Gaussian look to it. So this is some data and its power spectrum. Okay, let's just look at the intermediate function which I mentioned there, called a correlation function. So correlation function is very useful in many aspects of physics, in optics, in my field of neutron and X-ray scattering. It's a very powerful tool to understand a lot of things. So basically, it boils down to taking two points separated in your variable. So you've got sort of, this is x of t or x of r. I'll use, if r is space, because since we're already using x for the variable, and we're interested in taking some separation in one of these. Let's do it in time to start with. So I'll just call a separation tau, right? So, and then we're going to look to see whether the variable is at this point and this point are correlated with each other. And the simplest way of looking at that is to multiply the variables together, the value of x here with the value of x here. And then once you've multiplied, you can average over all possible starting points. So I can take a value here and here separated by tau as well. And that will be, that's basically a correlation function, and that's defined here. Okay, so we can define an autocorrelation function, which is basically a transform from our variable as a function of time to another function here. So we've taken the value at x, at t, and then t plus tau. So I'll go back. So this could be, let's say, t. And the other point would be t plus tau. Multiply them together and then average over all possible starting t's here. So we've averaged over t. We take some interval in time, and if we're doing an average, we normalize by the time range we've got. So this is a correlation function then from the variable, or more precisely, autocorrelation function, because we're correlating it with itself. So we multiply them together. Okay, so that's the correlation function. So one can prove a very useful relationship between the power spectrum and the correlation function, which is called the Wiener-Knitschen theorem here, which is basically the power spectrum, which would be, as I mentioned, as I had previously, Cx of omega, is a Fourier transform of the autocorrelation function. Okay. So I'll just show you a proof. I'll show you a proof for that in a minute. That's the Wiener-Knitschen theorem. But I want to just note one trivial thing that's but can be very useful is this result here. So if we've got an autocorrelation function, right, and we set the interval between our correlated points as 0, so basically we're calculating the correlation at the same time, then this thing here would just become x squared of t, and then we would average x squared of t, because we're doing this thing here. So the average value of x squared is always going to be the value of the autocorrelation function for tau equals 0. The separation between the 2 points is 0. Okay. So So okay, now you can look at the proof in your own time maybe, but here is the proof of the Wiener-Knitschel theorem, that the Fourier transform of the autocorrelation function is the power spectrum. So you can just go backwards from the power spectrum here. So this is the power spectrum. It's the, remember, it was the modulus of x omega squared is just the general power spectrum. So that's written here. And you can write that as the product of two Fourier transforms. And then you can, you've got Fourier transform 1 and Fourier transform 2. Okay. So we've just moved the variable and the phase factor of the Fourier transform here into here. You do a substitution to two new variables here. Let's get rid of this for substitution, and you can see once you've done the substitution, you can rearrange it such that this bit here is the autocorrelation function, and then this is the Fourier transform of the autocorrelation function, giving you the power spectrum. So we take the autocorrelation function strictly as autocorrelation function with if there's a complex number, you have to take the complex conjugate of one of the variables, and there you go, Fourier transform of the autocorrelation function gives you the power spectrum. Okay, so what I've done here is a two-step thing here. So here's the data I gave you or showed you, and here is its autocorrelation function. This blue curve, and one can read off from the autocorrelation function the value of x squared averaged here. Okay, and then I can Fourier transform the autocorrelation function and get the power spectrum here. This is the power spectrum. This is the Fourier transform of the autocorrelation function, and you can see that sorry, I just pushed a button I shouldn't have pushed. Yeah, so I put this, I forced it to have a certain correlation time here, you see, the data by filtering it, and that's why it's become, that's how it's arrived. Okay, so that's just an illustration of autocorrelation functions and the connection between the power spectrum and the autocorrelation function. So we've got the two useful results, which was the power spectrum and oh, actually, these are two more useful results. I'd forgotten that. So the first one was that, which I already mentioned, was that you can get x, the value of x squared averaged from, you can read that off from the autocorrelation function. The second one is actually, if we then if we take our Wiener-Knitschel theorem here, which was that the power spectrum is the integral of the autocorrelation function, and we integrate that again. Okay, so we integrate over the power spectrum, and then we do that integral on this one as well. You can show that actually this is the case. So the we've integrated the power spectrum, and then we get back the autocorrelation function. Okay, so that's just the, obviously, when you think about it, it's obvious you can do the inverse Fourier transform to get back to the autocorrelation function. But now if we take the autocorrelation function and substitute tau equals 0 here, we get the x squared. Okay, and then we substitute tau equals 0 on this side. Okay, and effect of it, interestingly, effect here is just to make this phase factor disappear if tau is 0. So now we've got an integral over the power spectrum. Okay, so the integral over the power spectrum is another way of getting the value of our fluctuating variable squared averaged over all times. Okay, so just to what does that mean? So here we've got this sort of fluctuations going around. Yeah, so if we want to measure how much fluctuation we have, one way would be to measure x squared average. So when we square the variable each time, we'll get some value and then average that. So you can see from just drawing some rough lines that x squared average might be about this amount. And that's a very rough and ready way of saying how many fluctuations you have, how much fluctuations, x squared average. But we can also get this x squared average by integrating over the power spectrum, the whole of the power spectrum here. So its power spectrum is symmetric in omega, so we can do the one-sided or two-sided integral. Okay, so that's basically making a physical argument for what you know already, that if there's lots of fluctuations, you'll see them in the power spectrum, and then you formally integrate over the whole power spectrum and get the amount of fluctuations. So here I've just done it again. I've integrated over this, and then I've got back this value, which was the amount of fluctuations that are in there. Okay. So here's my spectrum then, which is this broad thing with a system which fluctuates. And what I haven't said actually is that this system has a mean value of 0. So the mean value of x is 0, but it has a finite value for x squared. Okay, so now if I just add a constant to it, so the mean value is no longer 0, okay, and then do all my analysis again, I end up with, this is the power spectrum I end up with. This bit is the same, but now there's this bit here, which is actually a delta function at 0 frequency. So you know that the Fourier transform of a constant gives you a delta function, and that's all we're seeing here, something you knew before. But I just wanted to put that in context with fluctuation spectral analysis. So basically what it's telling you is that this integral here is going to give you the x squared average, and this peak here is your average, or if you like, you could say it was the average squared proportional to it. So this is basically the basis when you're looking at systems which order and have fluctuations, right? Because this bit here, this x value might correspond to an ordered moment that doesn't depend on time, and this bit here corresponds to fluctuations. It applies to anything, right? So one thing that occurs a lot in physics, right, is to resolve off fluctuations from static phenomena, so order of anything. And in order to do that, you need to have, you need to have enough resolution to distinguish between this fluctuations and this peak there for your relevant probe. All right, so that's a sort of just a phenomenological tools for looking at fluctuations and doing some Fourier transforms and seeing what how the fluctuating variable relates to different properties of the power spectrum. Let's now apply some of this to fluctuations and dissipation. Okay, so here is the paper from 1951, the celebrated fluctuation dissipation theorem in its most general form. And this connects spatially and time-varying fluctuations, the quantum mechanical ones, so zero-point energy ones, and thermal ones with response functions. Okay, we're not going to look at that paper. Let's just go back to the simple harmonic oscillator to illustrate things that I'm going to talk about now. So here's our ball in the liquid on its spring, fluctuating away. We measure its fluctuations. Okay. So in this case, we can define a susceptibility analogous to the spin or the magnetic susceptibility. So remember, the magnetic susceptibility was M over B. Okay, so in a generalized way, one can think of susceptibility here as being a displacement, a physical variable that changes when you put the perturbation on. So in this case, it would be the x divided by the thing that causes that displacement, which here was the field, and in the case of this mechanical example would be the force, right? Okay, so here we can define a susceptibility, which would be the displacement, the divided by the force, and I've written it in its Fourier transformed version. So this is for a time-varying force, sinusoidal force, for example, and then this would be the corresponding displacement. So we can define a susceptibility, which is a spring constant, effectively, for this system as well. Okay, so if we do that, we can work out from the equation of motion of the system, this damped harmonic oscillator, what this susceptibility would be. So here's the equation of motion. Then we've got an acceleration times the force, so F equals ma. We've got the force due to the spring here, which I've written. I haven't used the spring constant. I've just used the natural frequency of our system, and here this is due to the viscous force on the ball. So the viscous force, if I just remind you, what we're doing here is dragging a ball through a liquid. So we can use the Stokes force on a sphere. So that would be F is F is going to be 6 pi times viscosity times the radius of our sphere times the velocity of the sphere. So this is this term here. You see, this is a velocity. Here's a velocity. So this gamma, just to keep it simple, I've just had one constant here. This gamma is then going to be related to the viscosity and the and other constants. Okay, so this is the viscous damping term. Okay, so this is our mechanical equation that describes the this harmonic oscillator damped by the viscous force. So we can substitute in a trial solution. X equals x is proportional to e to the I omega for given frequency into this, and actually and then work out what the response function is, chi, and this is the imaginary part of the response function actually that you get. And what I'll show to you is that now so this response function actually has come, in this particular case, you see, from the viscosity, the mass, and the spring constant. And I'll show you that in this particular case, you get fluctuations, a fluctuation spectrum, which is this equation here. And you see we've got the same constants here, the gamma, omega naught. So this would look like fluctuations like I actually showed you earlier, so that sort of thing. This would be omega, and this would be the x omega squared. Okay, so this is basically a very simple, I've given you a sort of very simple illustration of the fluctuation dissipation theorem, where we've connected in this final result here the spectrum of the fluctuations with the dissipative properties of the system, encapsulated by this gamma, which is actually the viscosity in this case. So there's a connection between the fluctuations and the dissipation being viscosity. Okay, I'm not expecting you to get all that in one go, but this is just where we're going. So we'll come back to that in a minute, but let's just have a look at a bit of history. So this is basically building on, Robert Brown's observation of the polymer moving around here. The pollen atom moving around. We've got the atoms moving around, and the way those atoms move is connected with the viscosity, it turns out, and the temperature, and that's what determines this. Now, in fact, Einstein did many things. I mean, he's most famous for relativity, but he did some other things that were equally important. And one of the things he did is actually derive the first version of the fluctuation dissipation theorem. So Callan Wellin made the generalization, but the one that relates to the things I've just been telling you, the pollen and the harmonic oscillator, damped harmonic oscillator, is actually from the work of Einstein, so the first dissipation theorem. So the way he encapsulated it is, these are the equations from his paper here in the Allen de Physique. He looked at the case of the Brownian case, where the thing that you observe is the diffusion of the particle rather than the sort of fluctuations that I showed you in my example with the ball stuck to it, because that was easier to measure actually, because to actually measure these fluctuations, if we have a particle attached, it's very hard. You have to come up with an example where you can do that, but this could be measured. So Einstein connected the displacement here to basically the temperature, Boltzmann constant, and the mobility here. This is the velocity which the pollen molecule would move through if you applied a force to it. So the mobility is also connected to the viscosity. So if you work in semiconductor physics, for example, you come up with mobilities, but really it's the inverse of a viscosity. You imagine that you're dragging your electron through the system. So this is Einstein's fluctuation dissipation theorem that he showed. So it's a connection between sort of Boltzmann fluctuations and the particle moving. So it seems so simple. Okay, this is just to illustrate the connection a bit more between the fluctuation dissipation. So here's the fluctuation, as I showed you. You've got the particle moving, and the dissipation, the way you measure the dissipation is to drag the particle through with a known force, if you like, and define this mobility, which would be the velocity for the force. So this is the same type of equation used to define a viscosity. Okay, so Jean-Baptiste Perrin here actually got a Nobel Prize also for this sort of thing. So he measured the displacements of particles following the Brownian motion. So here's some of his objects that he measured, 365 of them, and then he looked at the distribution which they moved after certain times, and this graph shows that he basically verified the Einstein relation early in the last century. Another example of fluctuation dissipation theorem is the Nyquist theorem for electrical devices. Okay, so you remember I told you that you can define a susceptibility, and we defined it as a magnetization divided by a field, and then I said we can also perhaps have a displacement and a force. But you can also have a, let's say, a charge and a voltage, right? An electronic property, or and it turns out so this means that you can use these ideas of fluctuation dissipation also in electrical circuits, and you get this this equation here. So what we've got on the right-hand side is when people do electronics, they think of it this way. So we have a certain the variable that fluctuates here is the voltage. So let's put a voltage with an omega squared and a frequency. So what we've got is a resistor. Okay, and a resistor, of course, has electrons moving around inside. Okay, and when they move, if you apply, a voltage and they move in a certain, they'll have a certain velocity. They will eventually they'll dissipate energy. And we know that that's going to be proportional to the resistance and the current. So that's where the dissipation comes in. One way of seeing the fluctuations is to measure the voltage across a resistor here. And if you do that, you see these fluctuations, which is called Johnson noise, which is not actually written here. So that's a very simple way nowadays of seeing, the analogous thing to Brownian motion, except it would be related to the electrons in a resistor. Okay, so the spectrum would be flat with some cutoff, okay, which will be quite high in frequency. So very often in electrical circuits, you're interested in the noise for a certain part of the spectrum, right? And this is what the Nyquist theorem tells you. So that if you take out a little bit of the spectrum over some frequency range, delta nu, they've used nu here. Well, we can call this is the frequency rather than angular frequency. So the fluctuations just associated with this small range would be given by this equation here. So you can see it's the same equation actually, to within a factor of 2. So we've got R, which is conveying the dissipated properties. It's analogous to the viscosity, and then we've got a K, the Boltzmann constant, the temperature as we had, and then this range in frequency. So this is another example of the fluctuation dissipation theorem. So what we've got then is a whole set of connected things. Well, I've just mentioned a few of them. So I've mentioned the case of charge and voltage. So this is the Johnson noise. And then we had the position. This was the the ball, and then we can also have magnetism here. Okay, so what's the common connection between all of these things? Well, you can't just have any old pair of variables that you connect, right? We're connecting two variables through a susceptibility, right? So we've got chi, if I take the mechanical version, then is x over f. Okay, so that's your susceptibility, but these have to be a particular variables, and in particular, they have to be so-called conjugate variables, such that they add a term to the Hamiltonian like this. Okay, so we've got the displacement and a conjugate force. That's what we call it, displacement conjugate force, and the product of these two things has to give you an energy, basically, so that you add it to the Hamiltonian like this. Okay, so that's the from the mechanical example, we know that force times distance is energy, and then we've got a magnetic field times moment is also energy, and charge times voltage is also energy. So you can have other ones. So you can have electric, a dipole moment and electric field, and you could also have a current and a vector potential. That J dot I would also give you energy. Okay, so with each of these pairs, then you've got a fluctuation dissipation theorem, and there'll be somewhere in physics where you'll get the fluctuations that manifest themselves because of fundamental considerations which I've sort of been alluding to. Okay, so we've got the response function connecting these two. I think in the next bit I've called the response function alpha, so let's call this alpha instead of yeah. Okay, so that's just telling you what I've already mentioned. We can define a response function. I've concentrated in the lectures of just defining the response function in frequency. So we imagine that we define a response function with a certain time-dependent perturbation so that could be a time-dependent magnetic field or time-dependent force, okay? And then we can define the response function as the response is x to the force, and then this is the response function. You can also define response functions in actually directly in time, okay? So obviously, you can suddenly apply a force and the system will respond. Okay, but there is a complication there, is that it's not an equilibrium sort of situation where I've imagined that I've just had my sine wave applying my perturbation for all time, and I'm looking at the all-time response. But when you apply a force, obviously you have to apply it at a certain time, and then the system responds, and it can only respond to you will respond to forces applied before a certain time. So the response can only the effect of a force applied at a certain time can only apply to later times. So that has to be incorporated in your formalism. So here I've written down, so we've got the force, the response at some time. We go over, integrate over all times. Here's our forces that we've applied, and then this is our response function. So the response function, when we plot it out in time, has to look something like this. It has to take into account what's happened at previous times. So there's some properties to these response functions to do with that. It has to have this sort of shape, and one can work out one can work out what it should look like. So if you put this causality considerations into the response function theory, you can make some I haven't written them down. You can make some general relationships called the Cronus-Kronig relationships between the real and imaginary part of the susceptibilities or the response function. Okay, I don't want to say too much more about that because there's a lot to say if I start talking about it. But okay, so let's go. Let's look at the fluctuation dissipation theorem then in its most general form. So if we just go back here, I've told you have to have these two variables that are conjugate to each other, and if we go back further, we've defined correlation functions, Cxx of the x variable. So here is the fluctuation dissipation theorem for something where there's no spatial dependence. Okay, so what have we got here? This is it's a relationship between the power spectrum of the fluctuations. Okay, so this is the Cxx is our variable. The response function, in fact, the imaginary part of the response function. So remember, I showed you how you define a response function. We've got a Planck constant in here, and we've got the Bose factor, or a form of Bose factor here. It's not quite the normal Bose factor. One can write it, you can relate it to the normal Bose factor you have for bosons, but it's this is a factor that actually is including quantum and classical effects. So this is what Callan and Wellin showed in their paper. This is the fluctuation dissipation theorem in its full glory. The one that Einstein showed only included the classical aspects. So this is the thing that you need to understand fluctuation dissipation. It's the imaginary part of the response function. And I showed you earlier how you could get from, it's not so hard to take a damped harmonic oscillator and work out the imaginary part of the response function. So a damped harmonic oscillator turns out to be actually a good model for many systems. So if you can understand that, yeah. If you go to the classical limit for this thing here, then we get this this relationship here. Okay, and this is actually this chi double prime or alpha double prime for the response function of omega. This factor here is related to the viscosity, and that gets you back to the forms that we had in the Einstein situation. Okay, so let's have some just some examples, some of which I've already covered. So we've got the Johnson noise. So there's a bit more analysis of the Johnson noise. So one can write down the response function and then stuff it into the fluctuation dissipation theorem here and get the nice Nyquist formula here. So for magnetic fluctuations, then, if I jump to magnetic fluctuations here, we can apply the fluctuation dissipation theorem to the density, magnetic moment fluctuations, or and we can think about m as being our fluctuating variable, and b is the field, and the relationship between m and b is the susceptibility. This is the magnetic susceptibility. So then now this is the imaginary bit of our susceptibility. Okay, so if you wanted to understand more about this, you have to develop what this is. So here we have magnetic fluctuations, and here's our magnetic susceptibility. So you can add, if you like, a label to each of the modes that are fluctuating, a Q. You simply now do your spectral analysis for modes with a certain Q. So, for example, if this is Q and frequency, so here's some excitations, right? So you know, you can have an excitation like a phonon, and there'll be equivalent excitations like magnons, spin waves. which I'll talk about later in the course. So here's a spin wave, for example. So if we take this particular Q, and now we plot things as a function of energy up here, right? If we had a particular mode, the response function would have a peak at this point. So let me just draw that. So this, if I now had a spin wave, for example, and I had chi double prime, function of Q and omega, and I choose this particular Q, then my spin wave might have a response function like this, and this would be the pole, the frequency for that particular Q here. So this would be omega naught of Q. Okay, so if you go back to the let's quickly whiz back to the damped harmonic oscillator here. So when I went through this process here and got the susceptibility for my damped harmonic oscillator, this is what you get, the peak here, and this peak here is actually roughly where the pole of your excitation is. It moves with damping, obviously. So chi double prime will be peaked where the excitations actually are. That's why it's so important. Okay, so here's the peaking chi double prime corresponding to my excitation. So a way of detecting excitations, obviously, in general, is to let them absorb energy, and they will always absorb energy where the chi double prime, the imaginary bit, is the biggest. Okay, so now we're thinking about a single Q mode, and so we can apply the fluctuation dissipation theorem to this and work out the power spectrum, of the time excitations corresponding for that particular component of the wave, and then we can do it for all waves. Okay, so that's a bit of a something you have to get your head around if you do this. Okay, so the last bit, I wanted to just say a bit about scattering experiments, because this is actually a way of experimentally measuring all these things. So a little bit of a change of gear here. If we look at the fluctuation dissipation theorem, then on one side we've got the fluctuations themselves, and here we've got the response function, which is related to the dissipation in the system, and it remarkably connects the two things. So these fluctuations, we could measure these fluctuations by a scattering process. So if you scatter off a system, you can scatter off the order, and you can scatter off the fluctuations as well. That's what you'll see, and you can do that with X-rays. Here's the diamond synchrotron, or with neutrons. This is the Institute Larry Launcherman. So basically, experimentally, then you have a wave which we'll call K to distinguish it from the Q. This is for the neutron or the X-ray. It scatters, and you measure its change in wave vector and its change in energy, and that tells you something about the excitation that's caused this change. So basically, you can write Ki minus Kf equals Q for conservation of momentum, and then that will give you the wave vector of the excitation that's caused this thing, and the change in energy would be Ei minus Ef. You measure both of those, and you can measure your excitations. So scattering experiments, as I said, you can scatter from the fluctuations, so you can formally write a cross section actually like this. It's a correlation function of two variables. So this would work actually for phonons and for charge fluctuations and for spin fluctuations, anything like that. this is the variable that's this is what you call the scattering density, the variable you're scattering from, and this turns out that the scattering cross section is basically very closely related to the power spectrum. It's an asymmetric version of the power spectrum. So this side of it can be measured by scattering. Okay, and so this gives you a window directly to the response system here, if you do scattering experiments through the fluctuation dissipation theorem. The fluctuation dissipation theorem, you know, is a fundamental theorem. So it's not a theory or anything. This is a direct connection to the response functions. It's so direct that theorists would actually not, sometimes they won't distinguish between the correlation function and the response function. To them, because the fluctuation dissipation, the fluctuation dissipation theorem is just a mathematical proof, then so actually at a fundamental level there is not really a difference between these two sides. But physically, I've been explaining to you that you can see different aspects of the physics in each side. Okay, this is just summarizing some of the things I've said before. So in this very general case, then what we've got, we're thinking about two waves, as I started off with in the last lecture, a wave in magnetization and an applied perturbation. Okay, and we're relating these two things to give us this generalized susceptibility, and then we pop that into here. The quantum mechanics and the fluctuations come in, and that gives us the fluctuations, which we can then scatter from. And these fluctuations physical fluctuations, they can contribute to properties of the system, to heat capacity, to scattering, and so on. So this is what's going on. So I've just put in we'll put the transparency somewhere so you can see them. But this is just to show you that the damped harmonic oscillator is a very powerful tool for getting a good grip on these things. So here I've done what I mentioned was the case earlier in the lecture. Here's the overdamped oscillator, the damped harmonic oscillator equation, and you can work out the susceptibilities, the real part and the imaginary part here from those. Okay, this is the one that's relevant then to go into the equation, and I used that when I had the slide earlier showing the picture of the ball on the spring. Okay. I don't think I'll say much about the Kramers-Kronig, just to say that this bit is what we measure then, the imaginary bit, but if one can always get back the real part from these formal relationships, if you know the whole power spectrum, and in some cases that's very important things to do. Okay, and that's just illustrating for a damped harmonic oscillator. I plotted out the equations that describe it there. The imaginary bit is the bit that has the peak at the pole of the where the excitations are. So you might think the real bit is the bit that you want to use to detect excitations, but no, it's not. This is the imaginary bit, shows you where the actual excitations are. So this is just to illustrate the connection of the three different things I've been talking about today. That if a system has has some excitations, or these are just general excitations, which could be quantum levels in some atom, or spin waves with a particular wave vector. Here's your excitations. So the fact an excitation is there means that if you do the appropriate thing, energy can be absorbed, and you could measure the response function with respect to that shows that absorption of energy. and that can happen in many, many ways. As I showed you, you could drag an electron through a resistor or a ball through a viscous fluid, or you could shine light at something, glass or something that has absorption lines in from the atoms, and particular energies would be absorbed. So here we've got a connection between the excitations and dissipation or absorption, but we also have a connection between excitations and fluctuations. So because you have quantum mechanical effects, quantum fluctuations, and you have classical fluctuations, some of these excitations will always be excited, and that will give you the fluctuations. And the fluctuation dissipation theorem then connects these three different things. Okay, so that's it for this week. Are there any questions?
Yeah, so it's like I'm the only one here now.
What happened to them? They just disappeared.
Yeah, it's the thing with like online lectures, I guess. You can just leave and go. But so the imaginary part is what the imaginary part of the response is what is sensitive to excitations.
Yeah.
Because it's the non-linear part of the response.
It doesn't have to be non-linear.
Or just
actually, I know what you're meaning. No, it's the fluctuation dissipation theorem. The fluctuation dissipation theorem that I've showed you actually is the linear response. It has to be only the linear part of it. So it's a process that will absorb energy in the first order. So as we increase the field, magnetic field, or we increase the force which drags the particle through the fluid, then it has to be a process that is linear in increasing that force or the magnetic field. There will be a non-linear part to it, right? So obviously, if I, I apply a big magnetic field to the system, and its moment doesn't behave linearly with applying the field, that happens physically, but that's not what's relevant to the fluctuations. It's just the linear part. So there are cases, as you say, when the displacement squared or to some higher power is going to do that. But when you've got viscosity involved, the moment you start moving, you dissipate energy.
Okay.
Did that answer your question? So,
yeah. And
well, think of a resistor, right? Then when you put a current through it, it's that the dissipation is just proportional to the current. It's, it's proportional to the current squared. So okay, sorry, I think I misunderstood. I didn't think about your question hard enough, Charles. Yeah, so it's linear response theory in the sense that the displacement is proportional to the force you apply, or the voltage is proportional to the current. Yeah. But as you said, yeah, the energy that's dissipated will be proportional to the square. If you have a resistor, then the dissipation is going to be a half R times I squared, isn't it? So that's true. But you have to be in a regime where the displacement is proportional to the generalized displacement is proportional to the generalized force. So it's linear response theory in that sense. So what you said was correct, I think, at the beginning. Now you mention it, yeah.
Okay. Yeah, it's just, yeah. And what does so like the slide before, I think, is like, what does the real part of the, maybe, I mean, you plotted like real and imaginary parts of the response. It might be later. Yeah, that one. So yeah, the imaginary part is just the, you know, excitations. What's the real part? What does that show?
Well, yeah, that's a good question. The real part shows well, if I think the real part takes a bit more care to interpret, actually, but it does show you some things. So, but if we just start with the imaginary bit. So if you talk about excitations, then the imaginary bit is the bee's knees, in that it just shows, you know, basically how much energy is absorbed for each frequency. And if you've got an excitation, that picks out your excitation for you.
Mm.
Okay, so the real bit, the real part, I think, goes back to actually looking at what the system's actually doing for different frequencies. So one useful thing for the real part, for example, is if I take omega equals 0 in this diagram, you can see there's a positive intercept there. That's just going to be the force constant, right? So the 0 frequency real part is the force constant, you know, x over v, or it's the susceptibility in our case. Okay, and then when you come up to if you only have one type of excitation, and then you come up to the frequency, the resonant frequency, then you get this funny behavior where it flips from going up, you know. That's corresponding to the phase of the response changing, right? So when you're at the resonant frequency, then the response will be 90 degrees out of phase with the applied force. And so you get maximum absorption. And so the real part goes to 0 because everything's gone into the imaginary part. And then below, it's, you know, it's got one phase, slightly, you know, going at the same side, and then the other side, it's got a different phase. So it shows you how the phase of the response, if you set up that simple case where you're doing it with sinusoidal probes, it shows you how it changes as you go through it. Yeah.
Okay.
The real part. The other, what's the other thing? So the other place that the real part comes in is when you have like a model for excitation, and there's some sort of feedback, as it were, that comes into the feedback that you get that makes the excitation stronger. If there's some interactions, that often relates to the real part. But
okay, but all the exciting parts in the imaginary part.
Yeah, well, I think if you want to know where an excitation is, it's the imaginary bit. If you want to sort of see how much the excitation contributes to the power spectrum, it's the imaginary bit. But there are many probes that measure the real part. You know, if you're doing an optical measurement, for example, then you'll see these funny wiggle things, and people fit those. And so they get used to interpreting the data based on the real part, right? But physically, I think, you know, if you think that these are excitations, then the most natural interpretation is the imaginary part.
Okay.
But often if you haven't got access to the imaginary part, then you can start to interpret the real part in, yeah. But I think this is like a sort of cipher, isn't it? These two pictures, if you've got a response function, I think you can refer back to this. This is the simplest model for any excitation is the harmonic oscillator or damped harmonic oscillator, and that's where I would build on that to understand what we're doing. Like we're about to measure the phonons on I-2028, and we'll be measuring, basically this is what we measure, right? That's the great thing. We measure this when we do a scan. And you can see that from this equation. What's happened here? Yeah, so in the scattering books, then the basic thing is that this scattering cross section here is proportional to this correlation function, which is
is that not the case with Ricks?
Oh,
because I guess this is for neutrons, right? Or
yeah, so I'll answer that question in a minute.
okay.
So let me see. This is so in a very simple thing, I would say this was like m squared. Yeah. So actually, I think there might be a mistake here, but I think this should be an R. So basically, if you go to sort of level 2 or the next level of all this business, right? So you've got a correlation function. Sorry, no, what did I say? That's correct. So you've got a correlation function. Yeah, okay, so this notation here, so this is a correlation function, okay, of these two things, and then this omega and q is the Fourier transform with respect to time and space. Yeah, so this is formally correct, and that's related to this power spectrum. So yeah, so with neutrons, then the interaction at every point in the sample is very simple, because it's just related to mu dot b. But with Ricks, there isn't such a simple relationship. that's known. But the approximation that we're assuming is that there's some interaction, I guess, that as long as...
Yeah, don't they like approximate it with Fermi golden rule or something? If I remember correctly.
Yeah, well, this is Fermi. This is also Fermi golden rule. This approximation will be where you're scattering the proportional to this correlation function. That is essentially the Fermi golden rule, and you apply to neutrons. But the argument, I think, with Ricks is that so you've got, you've got some weird process happening on each atom, each site, right? But as long as there's some prefactor, there's some function, and then as long as it is proportional to the spin on that site, when you add up the effect of all the different sites together, this gets you a correlation function like this. It's just this factor out the front is much more complicated. If the different sites behave kind of independently, then you get a correlation function out. But if somehow that when the photon comes in, something happens at two sites at once, or something like this, then you start to get into trouble.
Mm.
But I think the argument in Ricks, is that you have this, and you hope that you have something like this times some other factors, basically, that are not, and that are not too energy and Q dependent. I mean, that's what we're trying to show. I think that's one why we do both neutrons and Ricks, to try and connect to see what the Ricks is actually measuring. But if you have, what we do know is that when we do have like a big peak, like here, that this shows through in the Ricks, right?
Mm.
Yeah, have you? That's So I mean the connotation is that we hope that some of this applies to Ricks.
Okay.
Okay. Is that anything else you want to?
I think that's all I want to ask for now. I mean, it's 12 now, so.
Yeah, there's a lot of stuff. Obviously, the other guys was too much for them then.
Yeah, I mean, it's the recordings available online, I guess, so just catch up with it.
Oh, okay. I was trying to make it a bit more general, because I think I don't know how much of this stuff you covered in your undergrad.
Not too much. I mean, I as part of the reading you gave me, I went through like White's book a bit, so.
Oh yeah.
Some of it, like the first lecture was quite familiar, and it's good to hear this like an intuitive description of like all this stuff though.
Yeah, but I think the thing to remember is there's Ricks on one side, but there's a whole bunch of other probes where the general ideas go across, like Raman scattering, for example. All this business, so if you look in the Raman scattering, then you also have this this factor is also there. This one here. What I didn't say is that this form I've given here is actually the general form. In this equation, like omega is different for positive and negative, right?
Mm.
So this Bose factor is not symmetric, and that's because of you know, quantum fluctuations also playing a part. So you can rewrite it sort of as a sort of n omega plus a half or n omega plus 1, actually, where you get you can get scattering. This at low temperature, right? This 1 means that you get scattering from the quantum fluctuations. So that means the particle can't gain any energy from the sample, but it can lose energy to the sample, and it scatters from the fluctuations that it sees. And that applies in Raman and Rix, I guess, and neutrons.